All right, so we're going to look at cylindrical shells, which is just another way to calculate a volume of revolution. They are actually used in cases where you can't use the Dr. T method, and I want to explain why. So it's when you have a funky region, and this is, I drew it symmetrical, but it's not. The question was to find the volume that's bounded by 2x squared minus x cubed and the x-axis, and then you spin it around the y-axis. And the problem is, if you apply the method I have, where I say, okay, like, let's punch out the hole, well, the hole is coming from the same function as the outer thing. So what you have here is a bowl inside that's being popped out, and the outside's like a mountain. And so it becomes really hard to do this the way I want to do it, because not only do you have this weird looking function, and it's only one function, you don't have two. Like I gave you some that had a line and a parabola, and the outer function was the parabola and the inner function was the line, but you have to still solve for x. It's a nightmare. So we use another method called cylindrical shells, and the method's pretty easy. But before we start, you still have to find the limits of integration a and b, and in this case, it's always where the picture starts and ends. And the picture starts when the curve is against the x-axis, and the picture ends when the curve is against the x-axis again. And that's where the curve is equal to 0. So I put little arrows here. And if I solve the curve equal to 0, I get a equals 0 and b is equal to 2, not a is equal to 2. X is equal to 2. So those are the 2 points. So your a is 0 and your b is 2. That's how you find them. So what's cylindrical shells? The idea is pretty simple. I'm going to slice this thing into pieces of rectangles. The rectangles, I'm going to label them as having width W. P is the distance from 0 to the center of this rectangle, and H is the height of this rectangle. If I spin just that one rectangle around, I get a keep cool. I call it a keep cool. I don't know what, I think each region calls it something different. But the keep cool is what you have around a soda to keep it cool. It's like I guess we usually use it for beer, but you have a little thing that goes around that you keep it cool. And so that there's a thickness to that. And W is the thickness of the keep cool. Anyways, I just want to find the volume of the keep cool. And the volume of the keep cool is easy. It's the outside of the keep cool minus the inside of the keep cool. And so I wrote a lot on here, but the radius of the outside is, I have a formula for it. It's going to be this P is to the center, and I need to go to the edge to get the outside. If W is all the way across, it's W plus 2. That's the radius. And I put it into the volume of a cylinder, which is what I have. I have if the keep cool and the soda can are together, the volume of the whole thing is going to be pi r squared h. And so I just put in my outer part, which is P plus W over 2. And then the inside, it's going to be, the radius is going to be P minus W over 2, because if P is all the way to the center, I've now slid over W over 2 amount. It's not really important, you know this is the actual derivation. I did some algebra now for outer minus inner. So I just subtracted the volume of the outer part minus the volume of the inner part. Algebra is not important. I found a lazy way to get to the answer myself using difference of squares. The point is that everything cancels, and I'm just left with pi h w times 2p. If I reordered the 2 and bring it out to the front, and I have the pi second, and I put the p and the h and the w side by side, I get what's in your book. W is the thickness of the keep cool, which it's the delta x, because I'm going to let that slide to 0. It's what we eventually in the limit get to call dx. P is going to be how far I am arbitrarily away from where I'm spinning around, which is x. H is, if you go back and look at the picture, H is the height, which is going to hit the curve. So H is f of x, how high I am on the curve. And I plug it all in, and then I sum up all those shells. The sum is the integral, and I'm summing from 0 to 2. This is my p. This is my height, which is the curve, 2x squared minus x cubed. The garbage was 2 pi. It's constant, goes to the outside. The width of my keep cool is dx. And that's how I get the volume without dealing with punching out holes and using cylindrical shells. This doesn't work all the time. It works when you can't use the Dr. T method. For everything else, you can use the Dr. T method. Hope this makes sense. You have concept questions on this, so this is why I went over this. The book talks about circumferences, and you can derive this using circumferences, but it's really, really confusing. The whole point is you're just taking a rectangle and swinging that rectangle around the y-axis, same way if you swung it around the x-axis, and you're calculating the volume of that shell and then adding up all those volumes together. That's really what you're doing.